Hello, thanks for coming. So we will talk about the two problems in homework 6 today. So, so it should be a very short tutorial. Yeah. So let's start. Yeah. Let me know if you have any questions. Okay. Eh? Ah, I made a mistake. So I should do this. Okay. So the first question is this one. So we have a set S, which is we call it the ground items. So we have a set of items. And then we also have a collection of the subset of S. So each subset inside this collection C will have exactly k items chosen from S. And then we want to show that if this collection of subset is not that many, so it doesn't have a lot of different subsets inside this C, then it is possible to color the items of S in 4 colors, so that we can make sure that every subset of this C, every item of this C, which is a subset of size K of S, is not monochromatic. So imagine, so for instance, if the C just contain exactly one size K subset of S, then it's easy. So we pick uh, 2 items in this as a subset, and then we color them differently, then in that case it will make this subset not monochromatic. So we see that if the number of subset of C is small enough, then it is possible to do the coloring so that we can avoid monochromatic thing. But on the other hand, if C becomes larger and larger and larger, so if we are collecting more and more and more a size K subset of S, for instance, if we have all the possible size K subset inside the collection, then in that case, we cannot avoid mono. So may, let me see, and then we don't know, So, but we at least we see that when C doesn't have a lot of things to consider, then it is possible to do whatever we want. And then how to show this is easy. We are going to use the basic counting method to do so. So let's see. What we are going to do here is that we are going to color the items of S randomly. So each of the item of S is going to be colored in one of the 4 colors. So there are a lot of different ways to do the coloring. Each item, there are 4 ways. So there are 4 to the power S ways of doing the coloring. And then somehow we want to show that at least one of these ways will allow us to make the desired result to avoid monochromatic subset. So let's see. Okay, so since we are doing the coloring randomly, now we can check that for a particular subset I that is in C, the chance that Si is monochromatic won't be a lot. So Si contains exactly k items, and then there are k and then there are 4 colors that we can choose to color the items of S. So maybe so let's say the colors are red, green, yellow, and blue. Okay. So Si can be monochromatic if all of them are colored in red, or all of them are colored in green, or all of them are colored in yellow, and all of them are colored in blue. There are 4 different ways that we can have Si to be monochromatic. The chance that Si is all colored in red, there will be a chance of 1 over 4 to the power k. And similarly, for each of the colors, yellow, green, and blue, it is also 1 over 4 to the power k. So in total, the chance that Si is monochromatic will be equal to 1 over 4 to the power k minus 1. Okay, so this comes from 4 ways of 1 over 4 to the power k. Now when C doesn't have many subsets, so less than 4 to the power k minus 1 minus 1, then the chance that a subset of C is monochromatic will be bounded to be a number strictly less than 1. So why is that so? So the probability of this to be true is equal to the probability of S1 is monochromatic, or S2 is monochromatic, or S3 is monochromatic, and so on and so forth. But by union bound, this probability will be less than or equal to the probability of S1 is monochromatic plus probability of S2 is monochromatic plus probability of S3 is monochromatic, and so on and so forth. So in that case, because there aren't many variations here, so this summation will be less than this number multiplied with this number, so it is less than 1. Okay, strictly less than 1. And this is all we need, because when we have this result, then we can find out what is the complement of this one. So this is the chance of a subset of C is monochromatic. So the complement of this event will be no subsets inside the C is monochromatic. So every one of them is not chromatic, is not monochromatic. So in that case, we can show that the probability of the complement, no subset of C is monochromatic, will be strictly greater than 0. Now, strictly greater than 0 means that this event must occur. Although it could occur with very few chance, but we don't care. As long as it occurs, this gives us the existence result. So we are done. So we are proving the original claim. We can color the items of S such that no subset in C is monochromatic. Okay? Good. So this is question number 1. Easy, right? And question number 2 talks about a tournament. So a tournament is a graph where there is exactly one directed edge between any pairs of nodes. So if we remove the direction, so it is a directed graph. But if we remove the direction of the edges, then it will be a undirected complete graph. So here, what is a tournament? So a tournament is simply, we start with a complete graph, undirected complete graph, and then we add directions, either forward or backward, for each edge. So there are how many tournaments of a graph with n nodes? So for a graph with n nodes, there are n choose 2 edges, right? So for each edge, there are 2 ways that we can pick for each direction. So the number of tournament graph with n nodes will be 2 to the power n choose 2. Okay, and here we want to show that for some tournament graph among these 2 to the power n choose 2 graphs, we can find one of them which contains at least a lot of Hamiltonian paths. Okay, and for this one, this time, let's try to use another easy technique called expectation argument. So how can we show this? Okay, so first of all, we consider a complete graph with n nodes, and then what we are going to do here is we are going to orient each edge randomly. Okay, so each edge will be in a certain direction with half of a chance. Now we have a graph, a random graph generated like this. So we now consider a permutation of n nodes. So for a specific permutation of n nodes, let's say the permutation is 1, 2, 3, 4, 5 up to n, then whether this permutation represents a Hamiltonian path. So here it means that 1 goes to 2, 2 goes to 3, and so on and so forth. We do not count the case that n goes to n minus 1, n minus 1 goes to n minus 2 up to 1. So this is considered in a different permutation. So the permutation 1, 2, 3, 4, 5 up to n representing a Hamiltonian path means that the directed edge between 1 and 2 is 1 points to 2, and then 2 points to 3, and so on and so forth. Okay, so for a fixed permutation P, then it is a Hamiltonian path with a chance of 1 over 2 to the power n minus 1, right? The reason is, for this fixed permutation, if it is a Hamiltonian path, we need all the edges, all the n minus 1 edges connecting them to be in the same direction, in the same forward direction. So this happens with a chance of 1 over 2 to the power n minus 1. N minus 1 comes from the number of edges here. And then inside this randomly picked graph, the expected number of Hamiltonian paths will be equal to what? So there are n factorial permutations, and then each permutation will have a Hamiltonian path with a chance of 1 over 2 to the power n minus 1. So here, y is equal, so this is the linearity of expectation. So expected number of Hamiltonian paths is equal to expected of whether the first permutation gives a Hamiltonian path plus whether the second permutation gives a Hamiltonian path, and so on and so forth. So we are forming indicators as what we are using all the time. So by linearity of expectation, we get this result. Now, because for randomly selected graph, the expected number of Hamiltonian paths is equal to this one, by the expectation argument, we know that there must be a certain object that has the number of Hamiltonian paths greater than or equal to this value. And similarly, we have a certain object with the number of Hamiltonian paths smaller than or equal to this value. Okay, so this is the so-called expectation argument. So once this is done, then we are okay. And indeed, we can modify this result to give to do de-randomization. We can really compute a certain tournament graph that has at least this many number of Hamiltonian paths in polynomial time. So I will leave this for you as an exercise, so you can use the de-randomization technique to really obtain a certain tournament graph that has at least this many Hamiltonian paths. Is that okay? Okay, so that's all for today. So, but remember, these two exercises are just talking about the basic techniques in the probabilistic methods. In the lecture, we have also introduced some more technique, like the second moment method and the conditional expectation argument. So if you have a chance, you may want to review what are the techniques there, because they are going to appear in the exam. Okay, so that's all for today. So let me check if you have any questions to ask. Let me see. Okay, and by the way, please also check the announcement that we have made about the homework 5 tutorial. So in homework 5 tutorial, there was a question, I think it is question number 4, that the description in the tutorial is not exactly the same as the description in the original assignment paper. So the solution given in the tutorial doesn't match with the solution in the original assignment question. So check them both. So both of them are correct with respect to the problems that are asked. Okay, check and then see if you really understand what is the difference and understand how to compute the result by yourself. Okay, so that's all. So this is going to be the last tutorial for this class. Perhaps I will make a tutorial about exam 3 solution after the exam. But but other than that, that's all the materials that I want to give you. So thanks very much for joining with this class and then staying with us until now, and then wish you good luck in the exam next week. Okay, thanks. Okay, bye bye.